So we have a last section of the isomerism, that is called the conformational isomerism, which is also considered to be the stereoisomerism. So conformational isomerism, it is happen due to the sigma bond rotation along the single bond. So like for example, if I am taking a alkane, so CH3 single bond CH3. This is, we have a ethane, and here the sigma bond can rotate, and because of this rotation we have a n number of conformer isomers, and these isomers is also named as rotomers. So here I am going to write that total numbers of conformers would be is equal to infinite, because rotation can happen any times, means n number of times, 0 degree, 1 degree, 2 degree, any degree we can rotate. Now based on this rotation we have a two type of projection here. So first is called Sawhorse projection, where the ethane is look like this. This is 2 carbon, hydrogen is 1, 2 and 3, and this one have the another 3 hydrogen. This is ethane. It's a conformational presentation, and we have another representation that is called Newman. Newman projection is look like suppose example, this is number 1 carbon, this is 2. So I'll make it that 1 as a circle, this is the carbon which has the hydrogen, 3 hydrogen, and the behind it number 2, which is represented by dot, and it has also the 3 hydrogen. So these are the two representation of conformational isomerism, Sawhorse projection and Newman projection. So like for example, if I am taking the Newman projection and rotating by any theta degree, let's say just assume the 60 degree, then in that case what is happening, the first carbon will be as it is, and the second carbon hydrogen will change the place and rotate by the 60 degree. So this angle which we are rotating, that is called the dihedral angle. So in general we could say that is the angle between the first carbon and second carbon hydrogen, that is the dihedral angle. It's an angle between CH bond on the front carbon atom and CH bond on the back carbon atom in Newman projection. Now let's draw the different type of the conformer of the butane. Let us understand the stability of these different conformers. However, we know that number of conformers are infinite only. So I'm taking the next example, that is called butane, CH3, CH2, CH2 and CH3. So technically I am writing this carbon and that carbon. This carbon have hydrogen, hydrogen and methyl group, and another carbon also have the hydrogen, hydrogen and methyl group. So I am going to write in terms of Newman projection. So this is the first carbon. I'll write methyl here, hydrogen is here and hydrogen is here. And for the second carbon, this is the dotted, Me is here, hydrogen is here and hydrogen is here. So when the dihedral angle is 0 degree, means Me is just behind of the Me, hydrogen is just behind of the hydrogen. So we can write the name of this conformer, it's called eclipse form. These are just a name, eclipse form of this conformer. Now I'm going to do the 60 degree angle, and 60 degree angle, whatever the conformer we are going to get, we have a name for this conformer, it's called a staggered form. So Me, hydrogen and hydrogen, and we have Me, hydrogen and hydrogen. So when we are getting the conformer at 60 degree, the name is become staggered form. On further rotation, one more 60 degree, it's called partial eclipse. It's not 100% hidden behind, so we could write the name of this, it's called partial eclipse. Now further 60 degree rotation, Me is just exactly opposite of the Me, hydrogen opposite, and this, in that case the name of this molecule, it's anti-staggered, when the angle between the bulky group is become 180. Next we have, again it's a partial eclipse, and then after each rotation we will get it this was the 60 degree, and if I do the 120 degree angle, then we will get it the eclipse form. So these are the different conformer or rotomers we got it. Now the question is, what is the stability order among these? So we have a eclipse, staggered, partial eclipse or anti-staggered. So technically anti-staggered, where you can observe here the repulsion is minimum, that groups are quite far away from each other, so steric hindrance is pretty lower. So we could say the stability order anti-staggered on the top, then we have staggered, then we write the skew or the gauge pattern. If the theta is 0 degree, we can write the eclipse. If the theta is 60 degree, we can write the staggered. If theta is any other degree, then we can use the name skew or gauge form. Can be 30 degree, 40 degree or any other degree. Then we have partial eclipse, and in the end we have eclipse. So that's a stability order where the steric hindrances become less in the anti-staggered, and in eclipse pattern steric hindrance is pretty higher. So those have the high stability, they have the lesser potential energy. So potential energy order is just would be reversed. So we can write inversely proportional to the potential energy of these molecules. So if we have to find out that is stability order in this diagram, so stability, obviously those have the higher potential energy, they are less stable. So A should be less stable, so we can write A is equal to C and B is equal to D, and stability B and D are equally stable and they are higher stable than A and C. Where if I write the potential energy order, so the potential energy order is just would be reverse, that A and C have the higher one. So here when the eclipse is rotating in terms of staggered form, so that during the rotation potential energy increases, and this energy is called the torsional energy, and that repulsion or the resistance in twisting is called the torsional strain. So I'll write the name here, it's called torsional strain. It is appeared due to the resistance of twisting, and the related energy is called torsional energy. So staggered theta 60 degree, here theta is equal to any other degree apart from the 0 and 60, and eclipse is reaching at around 0 degree. Now there is one very important note is coming, skew can be the more stable than the anti if the hydrogen bonding is appear. So suppose if I am taking example of the glycol, which is CH2OH, single bond CH2OH. So if I try to draw the Newman projection of this and the behind carbon, this is the glycol and it's an eclipse pattern, and if I do theta any degree apart from the 0 or the 60 degree, so we are getting in that case hydrogen bonding, and due to your hydrogen bonding, that is the skew is more stable than the anti-staggered, and then staggered, then a partial eclipse and eclipse, and this is happen whenever the hydrogen bonding is appearing. We have another example too, like for example if we have CH2OH and CH2F, they also can form the hydrogen bonding. So in that case also skew is a much better than the staggered or anti-staggered. Thanks for watching. For new updates, follow ChemTide. Thank you.